how's everybody doing? We're going to start with chapter 2 here, and chapter 2 is about the sky and the history of astronomy a little bit. So in our opening section here, we have the constellation Orion and the asterism Orion. We'll talk about what those two things mean. But we're basically going to talk about the birth of astronomy and how we think about the night sky. So we'll start with talking about what the sky looks like and how we talk about it, and then we'll talk about ancient astronomy in the past, astrology, if you're curious about what that is, your horoscope and zodiac, and then the birth of modern astronomy before we go into some stuff in chapter 3. So starting out, imagine if someone told you that the Earth was flat. How could you convince them that it was spherical? That's what you're going to see if you can think of a few things. Right now, when you look up at the night sky, it's hard to see all the stars that you could see with your naked eye. It kind of makes the stars an afterthought nowadays, so it's not as inspiring to look up. But throughout all of history, there were so many stars and so many objects that you could see with the naked eye, some nebula and some galaxies and fuzzy things and planets and all sorts of stuff. Humans spent a lot of time looking up trying to understand that. So we're going to try and think about those things and talk about how we understand the night sky today. So many folks today believe the world revolves around them and the heavens revolve around the earth. It's reasonable to believe that, and it was believed for much of history. This idea that the stars, the planets, the sun orbits the earth is called geocentrism, or the geocentric model of the solar system, or the Earth-centric model. So you imagine Earth at the center and the sun orbiting it. So we're going to talk about the history of that and the conversion to what's called the heliocentric model. So this makes sense, but it's not correct. This transition from the geocentric to the sun-centered or heliocentric model took place over a long time. Started with Copernicus, finished with Galileo, and we call it the Copernican Revolution. So we're going to talk about a history of that process from the early understanding of our place in the sky and the universe and to where we are today. So what we're going to hope to learn out of chapter 2.1 is define what is the celestial sphere and what are its main features. So you should be able to do that. You should be able to explain the system of coordinates that we use to describe the sky, and you should be able to describe how the stars appear wherever you are on the Earth, how they appear to orbit us depending on your location. And you should be able to describe how the motions of the sun, moons, and planets appear to us and how they change over time, and then understand the meaning of the term constellation. So think about a time you looked up at the stars at night. Whatever you saw was shared by thousands and maybe millions of people around the world that happen to look up at the same time. Everybody sees the same sky where they are and over a given night. It almost feels like you are under a dome. So you imagine looking up, you imagine there's just a large dome with stars stuck to it. And all the stars are just at the same distance and they're just stuck to that surface, like stars stuck on a ceiling. There's a important location straight above you. It's called the zenith. Your zenith is unique to you. Everyone has their own zenith point, so if you just look straight up above you right now, that would be your zenith. If you look at your neighbor and look above them, that's their zenith. So that's just a reference point. Okay? We use the word zenith when we're talking about where the sky is at the point where you are. Okay? Then along the horizon, the point where the sky meets the ground is called the horizon. It circles around you, and sometimes the sky or the horizon is hidden by trees. You can't see through the trees or bushes or animals or other things. A building, if you're inside, you can't see the horizon. But this is the idea. This is you standing here directly above you on the sky is called your zenith, and your horizon circles around you, and it's as far as you could see before the ground gets in the way. So the celestial sphere, if you lie down and you look up at the sky, which you would do if you didn't have Netflix, the sky would appear to turn over the night. The stars would appear to move across the sky. Stars rise from the east and set in the west, just like the sun and the moon, and they will move across the sky, across that dome, eventually setting behind the western horizon. This is if you're in the northern hemisphere like most of us are. Right now, all of us are. Ancient Greeks called this the celestial sphere, and they imagined it was a piece of glass with jewels stuck in it, and the stars were jewels, and they were flickering, and they were just on this dome that was rotating around us. Because what else could it be? Of course, it was that. We now know that the sky itself isn't what is turning. It's us that's turning. It's the Earth. The Earth is a basketball that's rotating. Okay. Imagine taking the Earth and shoving a stick through it, and then rotating it around that stick. That's called the axis of rotation of the Earth. There's obviously not an actual stick through the Earth, but the Earth rotates as if someone spun it like a basketball on a finger, and it's spinning around, okay? And there's a north and south pole to that rotation. This is kind of a diagram trying to show that. If you imagine a stick going through the Earth rotates around that north pole, okay? So that's going to sort of be our what we're trying to understand here. So this, you imagine this is you, your zenith point is somewhere above you, the North Pole is off this way, you're at in the northern hemisphere maybe, wherever you are, you're somewhere on the surface of the Earth. Your zenith will change. If you are standing here, your zenith would be there. If you are standing here, your zenith would be there, and so on. Okay? The Earth rotates around this point, like that. Okay? And this rotation is what causes the sky. So your zenith is right above you. You can imagine if the sky is rotating around, you had a star that was here. A few minutes later, the star is over here. So it appears like the star's rotating, or that everything's moving across your zenith a little bit. Okay? So the celestial sphere, Earth rotates once every 24 hours. That's what a day is. That's the day and night cycle. As we rotate, we turn towards the sun and then away from the sun. So the sun rises and then the sun sets. So as we turn towards the sun, and the sun lights us up, and then we go past the sun. At night, even as the sky rotates, the constellations and asterisms stay the same, and we're going to talk more about constellations and asterisms in a little bit. But the point is, all these stars appear to move across the sky, but they all appear fixed to each other. That's why it made sense to think of them as jewels in a sphere, and the jewels rotated, because it doesn't look like the stars move relative to each other, they just move across the sky. Even the planets on a given night, you'll find some planets out there that are usually the brightest stars on the sky. They don't appear to move night to night. They do move over time, but night to night, on a single night, they won't move relative to the stars enough for you to notice. So, in order to talk about all this, in order to communicate when I see something and you see something and who sees something, we developed a system of coordinates to do that. If you take the Earth's north and south poles and project them out into space, so if you were at the North Pole, your zenith would be the north celestial pole. You could imagine it going and sticking it to the stars. Those are called celestial poles, and they are the celestial poles of the celestial sphere. This is the north celestial pole from the North Pole, and the south celestial pole from the South Pole. Those are vocab words. Make sure you know those. And then you imagine taking Earth's equator, which goes down through the Caribbean, that part of the world, casting that out onto the sky. Then that becomes the celestial equator. So we're trying to create a coordinate system for the sky. This is basically what it is. You've got the Earth here, and you've got its north and south poles there, and then Earth's equator here. And then you can imagine this kind of sphere here as the celestial sphere, and you can imagine the stars appear from our perspective to be stuck along this surface. They're not actually stuck along the surface, but they appear to be. And so that's what we're going to use to try to describe our location. So if you imagine a star stuck there and we're standing here, we could describe its location. We could say, oh yeah, there's a star over here. It's this far up from the equator, that far down from the North Pole, and maybe this far over from some constellation, for example. So that's the celestial sphere, defined by the celestial equator and the north and south celestial poles. This is, if you think about it, that's a 90-degree angle, which is just two perpendicular lines to each other. So that means that this might be 10 degrees and 20 degrees and 30 degrees and 40 and 50 and 60 and 70, 80, 90, and then 100, sorry, not 100, up to 90 degrees there. So you can imagine dividing the sky up into degrees to get a location to talk about it. So we'll talk about how that relates to latitude and longitude right now. So this is Iowa, the state of Iowa. We are in Cedar Rapids right now, and we have a certain latitude and longitude. So our latitude is about 42 degrees north latitude. That's that line that goes through there. And then we're between 92 and 91 degrees longitude. And that's how we define, that's what GPS is based on, is finding a location on the latitude and longitude. 0 degrees longitude is defined in Greenwich, England, and then 0 degrees latitude is defined as the equator, and you go up to 90 degrees to the North Pole. Do the same thing with the sky. We have coordinates called right ascension and declination, and declination is like latitude. It's the horizontal coordinate, and right ascension is the longitude coordinate. And this is showing you we use degrees for declination and hours and minutes for right ascension. So if I click on this animation, you can see these lines here, 30 degrees, 25 degrees, 30 degrees. As we go 20 degrees, 25, and 30 degrees, as we go forward in time, you can see how the stars, for example, Betelgeuse, is moving, but not relative to the right ascension and declination. So what we do, we take a coordinate system called right ascension, declination, we stick it to the stars, and that way every star has a defined coordinate, just like GPS, just like latitude and longitude. So Betelgeuse or you know, any of these stars, they all have their own coordinate system. So the important thing here is, if you look down here, I'm fast forwarding time. You can see there's 6 hours there, 7 hours. That line is the 7-hour right ascension, 8 hours right ascension, 9 hours. It doesn't have anything to do with time. They just divided the sky up into 24 equal sections and used hours as the unit for that coordinate. So it's hours and minutes instead of degrees, but it's the same idea. It's just every star has its own right ascension declination. So if you had a star there, star here, they're all stuck, and then there's your your declination coordinate system, and then your right ascension coordinate system goes this way. So you would go from 0 degrees, 10, 20, 30, 40, 50, 60, 70, 80, 90, and then you would have your right ascension going like that around the sky. Okay. Okay, so circumpolar stars, some stars never rise and set. They simply appear to orbit around the celestial pole. Even if you are in the northern hemisphere of Earth, you will see stars appear to rotate around Polaris, which is the North Star. Polaris happens to be very close to the north celestial pole, so it doesn't appear to move. Stars that never rise or set are called circumpolar. These are the stars that make the star trail images look cool, and I'll show you a picture of that here. This is at the southern pole, at the South Pole. You can see the stars appear to rotate around the south celestial pole there. Okay, one thing to note, there is no star like the North Star, which we'll talk about here in a second, at the South Pole. This is at the North Pole, and there's Polaris. The North Star is right there, and Mount Fuji, and you can see the stars orbiting around, appearing to orbit around the North Star over a given night. You take your camera, long exposure, and just watch as the stars rotate around. You see they appear to circle around the North Pole. So that's the North Pole. I just showed you the South Pole. What about somewhere in between? Can you imagine? Oh, sorry, this isn't the North Pole. This is close. This is very high north at the altitude. But what happens as you move around on Earth? So, important point. The elevation of the North Star, if you find Polaris, the North Star, it tells you your latitude on Earth. It tells you what location you are around Earth. So for example, there's the North Star, and here's your horizon. If you measure up to Polaris, you measure that angle, and you find that it's 39 degrees above the horizon, then that's your latitude. So that's how you can navigate around on the planet, is by using that to measure your latitude. So if you want to stick on a latitude and drive or take a ship across the ocean, you want to maintain the same latitude as you do that. You're going to measure the location of Polaris as you sail across the ocean to make sure that you're always at the right latitude. So this is how the sextant is used to do that. It's got a mirror system on there. You measure the horizon, and then you go up, for example, measure where the sun is at noon, or measure where Polaris is, and then that will tell you what your, you read that angle, and that'll tell you your latitude. So the sextant is used for that. If you've ever seen one of these things, that's what you're trying to do, is measure the relative altitude of celestial objects, either the sun or, for example, Polaris. So circumpolar zones are the locations on the sky where the stars appear to be circumpolar, and that changes based on where you are on Earth, because obviously if you change your latitude, then Polaris is going to change, which means the area of circumpolar stars increases until you, and there's no south star at the South Pole, but when you're at the equator, okay, as you move from the North Celestial Pole to the equator to the South Pole, when you're at the equator, the poles are at either end of your horizon. And so all the stars appear to be circumpolar. All stars rise and set. If you are at the North Pole, every star is circumpolar. If you're at the South Pole, every star is circumpolar. And this picture here out of your book is trying to explain that, but I think it's better just to show this at the North Pole. All the stars, the North Star is right above your head at your zenith. It lines up. At the equator, all the stars appear to be rotating around. The poles are at the horizon there. So these stars, you'll see that they're not circulating around like the other picture we had, like over here in the at the South Pole. And if you're directly at the South Pole, then right above you is the southern celestial sphere, and all the stars appear to go around that point. Okay, so that's an interesting thing. All right, so the ecliptic is the apparent path of the sun as a year goes by. The sun doesn't just rise and set every day. You know that the days get longer, the days get shorter. So something else is going on. Right now we're in winter. There's like 1 hour of light, and then as soon as you wake up, it's dark. When you go to leave work, it's dark. It's dark all the time. So the star doesn't just rise and set. It moves across the celestial sphere about 1 degree per day to the east relative to the stars. This means that the sun rises later every day, and the path that the sun appears to take is called the ecliptic. Okay, this relative motion of it. Doing this again. So as the Earth moves around the sun lines up with different constellations during this path. As it appears to move across the sky, it lines up against different stars. These stars that it lines up with are called the zodiac, and they're the constellations that line up with the sun at that point. So you've got your 12 constellations here: Cancer, Gemini, Taurus, Aries, all these ones. You may know your sign, which we'll talk about, and that just has to do with if you were born right now in June, then the sun would line up with Taurus. So that would be your zodiac. That would be your constellation, that you would be your sign. If I was born in August, you might be Cancer or you might be Leo, depending on when in the month of August you were born. It's slightly shifting over time. So the ecliptic, sun appears to rise 4 minutes later each day. This path of the sun is actually 23.5 degrees tilted from the Earth's celestial pole. So the equator and the celestial equator are off by 23 degrees. The North Pole and the direction of the sun's orbit is off by 23.5 degrees because Earth is tilted a little bit as it orbits. So you can think of it this way. This is Earth. There's the North and South celestial pole. This is if the sun orbits around the Earth, that's where its straight up and down would be. This is Earth's equator, which lines up with the celestial equator. This is the apparent path of the sun. as it goes around. So you can see that they're 23.5 degrees apart from each other, and that means as the sun goes around, it's higher in the sky or lower in the sky. When it's higher in the sky, days are longer. When it's lower in the sky, days are shorter. We'll talk more about this to make this a little bit clearer. Okay, so that's the ecliptic. It's the apparent path of the sun across the sky over a year, and that's what makes the days longer and shorter. It's the reason we have seasons and so on, and we'll talk, like I said, more about that in a little bit, or next chapter. So, the sun isn't the only thing that appears to move across the sky. The planets also appear to move across the sky. Mercury, Venus, Mars, Jupiter, Saturn, easily viewable by the naked eye. The stars stay the same, but the planets wander among the stars over a day, over a month, over a year. So ancient Greeks, they look like stars, but we couldn't tell that they were anything different. They were just bright stars, and they moved. So they called these stars planets, which is the Greek word for wanderer. We have 7 days in the week because of this, because of the 7 wanderers: the sun, the moon, Mercury, Venus, Earth, not Earth, Jupiter, Saturn, and the moon. Did I say that? And Mercury. So there's 7 in there. 1, 2, 3, 4, 5, 6, 7. And then we have, it takes the moon 1 month to go around, so that's why we have the month. Okay, so constellations, what are they? If you divide the sky up into 88 sectors, these are called constellations. And constellations are, they're just like states. If you divide the United States up into 50 states, that's what we did. We divided the sky up into 88 sectors. If you put a picture associated with a constellation, like the Big Dipper, that's called an asterism. So the Big Dipper is the asterism for Ursa Major, or within Ursa Major constellation. So this is the Orion constellation. And you can see this white, kind of this lighter color. That is the Orion constellation. The asterism is this picture of Orion, the hunter, but the constellation itself is defined to be this actually very specific region of the sky. So if you ever read an article that says, in the constellation blah, that means whatever they were looking at is within this sector. This is Gemini, the Gemini constellation. You got the twins here. That's the asterism, but there is the very defined constellation of Gemini. Okay. All right. So that's constellation, asterism. Make sure you know the difference. So describe early examples. These are the learning outcomes for section 2.2. You want to be able to describe early examples of astronomy around the world. Explain how Greeks deduced that the Earth is actually round, spherical, and not flat. And also explain how Greeks calculated the Earth's size, and then describe what's called precession. None of this you have to know in that much detail, but you should be aware a little bit about it. And we also want to describe the geocentric model of planetary motion. So a brief history. Everybody knew the length of a year. They used Sirius, which is the brightest star in the sky, to track. They watched as it rose and set and wind, and noticed that it corresponded with the flooding of the Nile every year, so they would use that to try to manage their farming operations. Ancient Chinese had a working calendar. They recorded astronomical objects. The Mayans had a sophisticated culture around astronomy. The Polynesians navigated hundreds of miles, hundreds of kilometers of open ocean using the stars, so they were sophisticated at being able to navigate that way. And Aristotle believed, so there's a big history of this stuff, and Aristotle believed the Earth was round because of 2 ideas. Number 1, during eclipses, when the Earth goes between the moon and the sun, you can see a curved shadow, which indicates that Earth is at least a circular disk. If it's flat, it's a circle. But also the North Star changes based on your altitude. So we talked about how the circumpolar stars change and the North Star changes as your altitude. That can only be possible if the Earth is a sphere. If the Earth was flat, it wouldn't matter where you walked. The North Star would always appear to be above you. So that was his reasoning that the Earth was round. So this is a picture of, you can see the curved shadow here as the moon goes, as the Earth goes between the Earth. As the moon ends up where the Earth is between the moon and the sun, creates this shadow. Eratosthenes realized that he could estimate the size of the Earth by measuring, doing some geometry here and measuring basically a slice of the Earth like that to measure its radius. And if he could measure the distance of this curvature, he could get the distance to the center of the Earth. And that was the main thing. So how did he do that? Well, he said if the sun is here, then the rays would be would not be parallel, and he couldn't use the sun as his target. But what they realized is that the sun was far enough away that the rays of light hitting the Earth against the surface are mostly parallel to each other. That means that you could use the sun here to make straight lines coming in, and if those straight lines were coming in, then he could use poles sticking out of the ground, and then he could actually measure the angle of the shadow cast by these poles. So basically, he created a well at this location where the ray went straight to the bottom, so he knew he was lined up with that with the sun, basically directly at the sun. And as he went along the surface of the Earth, since the Earth was curved, these poles started to make cast shadows. And the further away you were from the equator, the less direct the sunlight was. Not the equator, but the Tropic of Cancer. Okay, and so he figured this out, and by measuring that angle, he could measure the angle down here. And by measuring that angle and the distance you walk here, there's an equation that relates this angle to that distance and this arc, and he could figure out the radius of the Earth and how round it was. So that was pretty cool. All right, so Hipparchus was one of the most famous astronomers. He lived in present-day Turkey a long time ago, and he made a lot of detailed measurements, and he realized that the North Star, the location of the North Celestial Pole, actually changes over time, and that is called precession. And precession is when the North Star changes over time. So right now it's lined up with Polaris, and over time it'll be here, and then closer to Deneb, and then Vega, and then so on over time. So you can see back in 5000 BC, or in AD 1, the location of the North Star is slightly different. It changes every 26,000 years. It takes, so 26,000 years from now, we'll be back to Polaris. Yeah, so this is what happens. The Earth is rotating, but it's also got a wobble to it, and that wobble is called precession. So you should just be aware of what precession is, and it's a wobbly, when you flip a quarter, or spin a quarter on a table, it's nice and uniform spinning, but as it starts to slow down, it starts to wobble crazy, or a spinning top starts to wobble. The Earth has a little bit of wobble. So it rotates 24 hours, but it's also got a kind of an unsteady wobble to it. And you can imagine it's floating in space, doesn't have anything to hold on to, so a wobble is not that unusual for a thing. Okay, so that's what's happening. So right now we're lined up with Polaris, and over time we'll be lined up with these other stars, and there will be a period of time in between where there isn't a clear star at the North Celestial Pole. All right, Ptolemy lived in the 140s, the most famous for his amalgamation of astronomical facts. He created a system where you could predict the location of the planets. His system lasted for 1,000 years until Copernicus and the Copernican Revolution. This was Ptolemy's explanation of the orbits of the planets. He imagined the Earth was the center, and the planets orbited around the Earth doing this little dance. Okay, it's a little weird, but it worked. So let's talk about section 2.3 to explain astrology, explain what a horoscope is, and summarize why it's not a scientific practice. And then we'll come back to Ptolemy. So that's your just initial foray. We'll talk about Copernicus here in a second. So astrology is when you try to predict what happens based on the location of the planets. It started a long time ago. The Greeks believed the stars affected every individual. The Babylonians believed they only affected kings. The horoscope is a chart. It's showing the positions of the planets in the sky at the moment of your birth. And the word horoscope means time watcher, which you can use as marker of the hour. There's 12 zodiac signs, like I talked about earlier. Your sign is the zodiac sign that the sun was aligned with at the moment of your birth. The precession of the Earth, like we just talked about, affects this. So we've slipped the location of the zodiac has changed by 1/12, or about one sign from when it was originally imagined. So these are the signs. I am a Leo, which has some implications, I suppose. Your horoscope is, they try to predict what will happen to you, based on when you were born, where the planets are, and so on. Today, there's no evidence that there's any way to predict that. It's better if you're a kid to get a lot of hugs and nutrition, and that will have more effect on your performance and behavior and personality as you get older. Have good role models. Okay, so that's my aside on astrology. So take it or leave it, whatever. Modern astronomy now. Copernicus and the heliocentric model. We want to explain the Copernican model. We want to describe Galileo's discoveries, and we want to explain how Galileo tilted the balance in favor of the Copernican model. So you want to be able to understand basically what the Copernican revolution is and why it's important. Here he is. Looks like I painted that, maybe. Maybe that's what he really looks like. I don't know. The Copernican model. Wow, look at this. It's a little bit different. The sun is the center, and all the planets orbit the sun. When Copernicus came up with this, there was no reason to do that. He just liked it better. And this is a comparison of the Copernican model on the left here and the Ptolemaic model here on the right, where you can see Mars has to do this little dancey dance whoop, 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 to explain and predict its orbit. One of these things is better than the other. One is simpler than the others, and by Occam's razor, you generally want to go with the explanation which requires the fewest assumptions. In this model, you have to assume the planet does this little dance. In this model, you don't have to assume that. If Earth orbits the sun and not the sun orbits the Earth, then everything makes a little more sense. But this heliocentric model was difficult to prove one way or the other, and since they both predicted when and where the planets would be, nobody really worried about it. Enter Galileo, and there's Galileo's telescope there. He used the newly invented telescope, and the telescope that he invented, he didn't invent it, but he took it and he was the first one. Instead of using it to look for pirates and land, he used it to say, oh, let's look at a star up close. And what he discovered was the phases of Venus. Now, phases of Venus, that means it has phases of the moon, or it has phases just like we see phases of the moon. The moon can be a full moon, it can be a crescent moon, it can be a quarter moon, and so on. Same thing. Venus can be full Venus and all these crescent shapes, and you can only explain that if Earth is between, if Venus is between the Earth and the Sun, and Venus orbits the Sun. Okay, so the only way you can explain that is this. So this was some of the best evidence that the Sun was the center, and we both orbited it based on the phases of of Venus. So this was a really big deal, and that was the true beginning of modern science, was Galileo really making astronomical observations with the telescope and taking detailed notes. So he discovered a lot of things that we're going to talk about when we talk about orbits and gravity, and when we talk about Jupiter and its moons. He discovered a lot of things related to that. But this discovery of the phases of Venus made it very difficult to argue against the heliocentric model of the solar system. This period of switching between the Ptolemaic view, the geocentric model, and the Copernican view, or the heliocentric model, is called the Copernican Revolution. So just be aware of what that is. And that is all we have to talk about today. So I will see you guys later. Again, leave some comments below if you have more questions about this stuff you want me to talk about next time. See you guys later. Bye.